Brittle to ductile transition and fractures in steel.
The goals of this experiment is to gain knowledge and experience in operating the Charpy impact testing machine. Also to understand how temperature affects the fracture mode of a material, in this case the 1018 alloy steel. How to distinguish between brittle and ductile failure surfaces. And finally to determine the brittle to ductile transition temperature plot. It is very important that we study this topic today, as the most sophisticated structure we have today is still susceptible to brittle or ductile fracture failure. There are cases throughout history across the world, but specifically the United States, where there have been great loss of life due to these failures. In 1919, there was the Great Boston Molasses Tank Disaster, in which 12 people were killed and 40 injured. In 1967, the Silver Bridge collapsed in West Virginia, killing 46 people. During World War II, the merchant ships Liberty, in which over 2,700 were built, over 250 of the ships cracked or fractured, and 19 were completely broken in two. Due to the work in Cambridge by a woman named Constance Tipper, there was established a critical temperature below which the fracture in steel changes from ductile to brittle. When she looked at the fractured Liberty ships, she realized that the cause was not from the welding, which was the initial thought, but it was caused by the steel itself. She showed the people that there was a critical temperature below which the fracture mode in steel changed from ductile to brittle, and because the ships all traveled to the North Atlantic, where the temperatures are rather low, they made it more susceptible to brittle failure. The fatigue cracks were able to spread rapidly across the fused metal of the ship's welded joint plates, and instead of being stopped at the plate edge of a riveted joint, they continued on, causing the catastrophic failure. Ductile fractures occur with plastic deformation. The energy is usually absorbed before fracture. Materials with these types of fractures usually show large amounts of physical deformation. The crack propagation is relatively slow, and the fracture is one piece with large deformation. Surface is usually rough due to large amounts of plastic deformation. Brittle fracture has little to no plastic deformation. There is no energy absorbed before fracture. The cracks propagate rapidly through the material, which leads to catastrophic failure. The brittle fracture is very material dependent, but it usually occurs at lower temperatures at high strain rates, and the fracture surface is relatively smooth. Materials undergo transition from brittle to ductile fracture as the temperatures increase. The temperature for transaction depends upon a couple different things: the chemical composition and bonding, the microstructure, and the kind of test that is performed. The temperature could be very high for ceramics. However, the transition temperature also can be very low, as is in the case for stainless steel alloys developed for cryogenic applications. Our experiment consisted of 7 ingots of the 1018 alloy steel with dimensions of 1 cm by 5 cm with a notch on one of the long ends. Initial hardness of each sample was measured. Then, using a stamp, each sample was given a unique tracking number. Each sample was then given a unique heat treatment, ranging from an oven at 160 degrees Celsius to immersion in liquid nitrogen. The temperature profile of each surface was measured prior to testing. Then each sample went through the Charpy impact test, and the force was recorded, and we inspected each sample to see what kind of damage was done. To see the rest of our results, please continue on with this presentation. For this brittle to ductile transition temperature experiment, the following equipment and supplies were used. The specimen used is a 1018 alloy steel, hot and cold rolled. All 7 samples were ran through the same Charpy impact tester pictured below. Due to design restraints where the tester was located, a correction factor was needed after the readings were completed. We found that we had to correct each reading by subtracting 11 foot-pounds from the initial reading after the test was complete. Calipers are used to measure the length, width, and thickness of each of the 7 samples. Readings are taken at several different points in this experiment, and all data is recorded for later data analysis. Glass beakers are used to hold the solutions that the 7 samples will be sitting in prior to being ran on the Charpy impact tester. The infrared thermometer was used to measure the surface temperature of each of the 7 samples just prior to being ran on the Charpy impact tester. The thermometer on the right was used in various glass beakers to measure the temperature of the bath solutions that some of the samples sat in prior to being ran on the impact tester. The hot plate is used to boil water for one of the samples, and the oven was used at a couple different points in this experiment. First to run some annealing tests prior to the Charpy impact test, and then for the Charpy impact test, one of the samples was ran at 300 degrees C. For the extreme cold portion of the experiment, we used liquid nitrogen and dry ice. Other supplies required are salt and ice mixture, which was required for one of our samples, masking tape, metal stampers, which we used for identification purpose. Each of the 7 samples had a unique stamp, and finally tongs to safely handle the samples that are extremely hot or cold.
For this experiment, we tested 7 samples, each of which were placed in a different medium in order to bring the samples to different temperatures. The temperature of our samples ranged from -196 to 157 degrees in order to give us enough of a range to find the brittle to ductile transition temperature and to see how impact energy changes with temperature. Pictured here are samples 1, 2, and 4, the samples in the furnace, boiling water, and salt water. We didn't show the room temperature sample. Pictured here are samples 5, 6, and 7, the samples in dry ice, liquid nitrogen, and ice water. The Charpy machine determines the energy it takes to break a sample by swinging a hammer like a pendulum into the sample and breaking it. In order to operate the machine, first the hammer is lifted and clamped in place. Next, a sample is placed in front of a slot in the anvil with the notch facing forward, so the material will break at its center when the hammer strikes it. Finally, the hammer is released so it falls and collides with the sample, breaking it and then continuing along its path through the slot in the anvil. The Charpy machine is able to measure the energy that it took to break the sample due to conservation of energy. The hammer's energy after it breaks the material equals its initial energy minus the energy that it took to break the sample. Because the hammer behaves like a pendulum, its amplitude is proportional to its energy, so we can figure out the initial and final energy of the hammer, and from there, the material's impact energy. Luckily, the Charpy machine reports this energy by having the hammer swing move a needle and a gauge, so the machine's operator does not have to do these calculations.
Sample 1 from the furnace had mostly ductile fracture because of the large deformation across the surface before failure. Sample 2 from the boiling water had mostly ductile fracture as well. There was considerable elongation along the surface prior to the brittle fracture. Sample 3 was room temperature and had a mixture of ductile and brittle fracture, almost even split. Sample 4 was from the iced salt water bath and had majority brittle fracture, very slanted and smooth surface. Sample 5 had the same result on dry ice, had a very smooth fracture surface. Sample 6 had a very abrupt brittle fracture, and sample 7 from the iced water had a relatively brittle fracture, almost completely flat.
The temperature versus impact energy plots of the 1018 and 1045 steel are similar to the shapes of the plots that came from the Callister book. From the graph, you can see that the more carbon the sample has, the lower the impact energy. This is because as the number of interstitial carbon increases, this hinders dislocation. This causes the material to be more brittle, which lowers the impact energy needed to cause failure. The graph also shows that as temperature decreases past the brittle ductile transition temperature, BDTT, the impact energy rapidly decreases, meaning the steel has a higher chance of shattering instead of deforming when the temperature is lower than the BDTT. In conclusion, as temperature decreases below the brittle ductile transition temperature, the steel is more likely to shatter than deform. The more carbon that is in the steel, the more interstitial carbon atoms there are. These carbon atoms hinder dislocation movement. This causes the steel to be harder and more brittle and also have a lower brittle ductile transition temperature. A ductile fracture surface will appear rough because there's a lot of plastic deformation. A brittle fracture surface will appear smoother and have a more distinct break. Some of the possible sources of error from our data collection are cooling or warming time, which is when the sample is taken out of the medium to be placed on the Charpy machine. Placement of the stamp. The stamp should be adjacent to the V-notch. Placement of the sample. The notch should be centered on the machine. Temperature measurement of the sample. There could be parallax error or not placing the probe in the correct spot.